No, there are two different ways for correlation clustering. I mean, many different ways, but two of the most important ones are Lambda correlation clustering and Motif correlation clustering. This is about hypergraph. And so hypergraphs are very important. For example, you can generalize everything from graph to hypergraph. For example, there is a guy called Rafael Mulas. He is in Alan Turing and Max Planck. I think she is in Alan Turing, and she used Cheeger inequalities are generalized to the case of hypergraph. And there is another guy, Karthik Chandrasekaran, and he used hypergraph k-cut for fixed k in deterministic polynomial time. And but now I want to talk about Lambda clustering, Lambda correlation clustering. We have talked about correlation clustering in previous lectures. Now, a very interesting way to generalize all of these correlation clustering is the framework of Lambda clustering, correlation clustering. As you know, positive mistakes in Lambda correlation clustering for positive mistakes, so it is not balanced, it is unbalanced. For example, we say we care about positive more than negative, 1 minus lambda cut of S. And for negative mistakes, we say that it is lambda E minus 1 minus lambda SS bar minus cut of S. And so if you sum, the total weight of mistakes is equal to cut of S minus lambda SS bar plus lambda E minus. And so this is our objective. And everything is related to this. For example, if lambda is such that the cut of S minus lambda S bar is less than 0, then the sparsest cut problem, which is equal to minimum of cut of S over S plus cut of S bar over S bar. So if you put that, it becomes just V cut of S bar S, and this just becomes sparsest cut problem. On the other hand, if lambda is very, very big, even bigger than much bigger than 1 minus lambda, so it leads to a cluster deletion problem. Cluster deletion problem. It means you cut edges and we form cliques, lots of cliques. And it turns out that it is a spectrum of problems going from lambda from 0 to 1. For example, if lambda becomes rho star, it is the normalized cut. So it's a framework for those who like general things like unique game conjecture, SOS, and those things. It's another general formulation of many problems in computer science. So if lambda star is this, it becomes sparsest cut. I mean, and Nate Welt in his PhD thesis described these things, and so you can read his thesis in Cornell in 2019. And 1 over 2 is just modularity. So you see, you have lots of different problems. 1 over 2 is correlation clustering. So it is also called cluster editing, 1 over 2. For example, here M over, so it becomes cluster detection problem. So lots of problems. So it's like a spectrum of problems. But if we go to lambda to 0, when you get closer to that, you have fewer but large sparse clusters. Fewer, larger, sparse cluster. If you go there, you have many small dense clusters. Dense clusters, but very small. Many small. And also, for general weights, what we have, there are some results for general weights, for lambda correlation clustering, and unweighted correlation clustering. For unweighted correlation clustering, we know that we have 2.6 factor approximation times, minimum number of mistakes, of course. And for lambda correlation clustering, we have got two approximation. The work of Nate Welt, we have two factor approximation if lambda is greater than m over 1 over m. And we get three approximation if lambda is greater than 1 over 2. And for general weights, so it is very bad that it is just log n. And this is the best approximation that we know. For example, for minimum of f lambda of x in correlation clustering, you can write it as xij plus lambda 1 minus xij ij. And it satisfies the triangular inequality xik plus jk. Also from xij, that is 0 and 1, same as usual, you relax it to any real number between 0 and 1. So that was about introduction to lambda clustering. And the other one was motif clustering, that I said motif correlation clustering, that I said it is related to hypergraph clustering. But as you know, they are not good results. All of them are greedy. We have many greedy algorithms for hypergraphs, but and they are not proved because it is just greedy and nobody cares about. Nobody knows really how to rewrite. It's like something like residual graphs. It's a good idea, but you cannot analyze it easily. It's very hard to analyze it. So it's the same problem. In motif, in hypergraphs, let me give you some examples of hypergraph and why they are important. For example, the problem of posts and tags. It means that when you post something in LinkedIn, there are a number of posts, and you add some tags. For example, I write machine learning or computer science or graph theory. And the tags, post one is a node. Post 3, post 2. So this is a hyper edge. Another edge could be post 4, for example. It's like an edge because it consists of only 2 vertices. Also, you may have post 5 and post 6. So this can be another hyper edge. And these hyper edge, all of the vertices inside that corresponds to tag machine learning, tag ML. For example, this is tag computer science, and this is tag computer science and ML, for example. If they have intersection, but here we don't have any intersection of them. But another example could be students and class. For example, student 1, student 2, student 3 it's in a hyper edge. They correspond to class machine learning class. And student 2 and student 4, student 5, all of them are in a computer science class. But these two students also attend pure graph theory. So another class, S6, X7, and student 8. So these are two examples of hypergraphs. All right, so have a great weekend.